Hello students, let us start our today's session with alkenes from the chapter hydrocarbon. Alkene, it has a doubly bonded system and both the doubly bonded carbon atoms, they have sp2 hybridization, and that alkene, it may contain one or more doubly bonded carbon-carbon atoms. So depends on the number of double bond present in an alkene, that can be called as alkene, dialkene, trialkene, etc. So let us discuss about the sp2 hybridization of carbon atom that is involved in alkene system. How the sp2 hybridized orbitals are produced? Carbon, it has 6 electrons. That atomic number of carbon is 6 and whose 2 electrons are the part of helium structure, and the rest of the 4 electrons that occupies 2s and 2p orbital. The 2s, it has 2 electron, 2p orbital, it has 1 electron in each of 2p orbital. So in their ground state to excited state, the 2s orbital that shifts over to mixing with the 2p orbital, so that forms sp2 hybrid orbital along with one more electron left in 2p atomic orbital of carbon. These 3 sp2 hybrid orbital of carbon, it gives rise to a trigonal planar shape for the carbon atom. But in an alkene, we need at least 2 carbon atom to have a doubly bonded system. So we need to take a 2 carbon atom where both of them are having that sp2 hybridized orbital and the trigonal planar structure. So let us take the 2 carbon atom with trigonal planar shape of both of the carbon atom. And both carbon, they have 3 electron. So one of the electron is shared among. So we can write both the 3. For both carbon, we can represent 1 electron of this carbon, and this sp2 hybrid orbital, it has electrons in their 3 of the sp2 hybrid orbital. So both carbon atom, they are sharing its one of the sp2 hybrid orbital to make carbon-carbon sigma bond. And both carbon, they have 2 more sp2 hybrid orbitals which are shared with the 1s1 hybrid orbital of hydrogen. So that also gives rise to a sigma bond. So we may find there are 4 sigma bond with carbon and hydrogen and 1 sigma bond between carbon and carbon. So let us find what about the 2p orbital, that means which is not taking part in hybridization. The 2p orbital of both carbon atom that lies over the plane which is perpendicular to the plane of the system, and both of them, they have 1 electron in it that undergoes sideway overlapping and gives rise to a pi bond. And this pi bond that lies just above and below the plane of the structure, so we can represent the pi bond such a way. And moreover, these pi electrons are a delocalized electron. What is called delocalization? The pi electron that can move between among more than 2 atoms. Such delocalizations is possible only in carbon-carbon doubly bonded or the system with the pi electrons. So because of this delocalization of pi electron, that can develop the charges among the bonded carbon atom, and it becomes the more electronegative of carbon because of sp2 hybridization. The S character compared to sp3 is greater in alkene. So when S character increases, electronegativity of that particular carbon also increases, and hence they can easily be attracted by electrophilic reagents. Electrophilic reagents are the electron seeking group. So and during this they may undergo addition reaction where alkenes are converted into alkanes. Now let us consider about the bond length of carbon-carbon in alkene with the bond length of carbon-carbon in alkane. See, carbon-carbon bond length in alkane is found to be 154 picometer, but in the case of alkane it is found to be 134 picometer. Why the difference in bond length? See, Compared to single bond, the double bond length is decreases. So, when bond length decreases, the strength of the bond increases. That is what? The number of bond between the system is said to be bond order. Here, the bond order of alkane is 1, but the bond order of alkene is 2 because it has 2 bond between the carbon atom. So, when bond order increases, bond enthalpy also increases. So, carbon-carbon single bond enthalpy is found to be 348 kilojoule per mole. But in the case of carbon-carbon double bond, the bond enthalpy is found to be 641 kilojoule per mole. So, bond order increases, bond enthalpy also increases. But the reactivity of alkane is high compared to the reactivity of alkane, because both carbon atom in alkane, they get their octet structure. But in this alkane, it needs to get 2 more electron to get its octet structure, because one of the pi electron is shared among the carbon atom. They are not belonging to one of it itself. So, it needs to take 2 more electron to get their octet structure, and hence alkenes are more reactive than alkanes. And the alkenes are generally known as olefins. What do you mean by olefins? So, we said alkanes are paraffins. Paraffins means it shows little attack towards other compound or the reactivity. Olefins means they able to form oil. They exist in oil form. So, such alkenes are said to be olefins. The next topic of alkene is nomenclature. So, how to name the compound? First of all, we have to identify the longest chain. Then we have to identify the position of double bond, and you should write the alk plus ene. To write the name of the compound, we need, if it has any substituent, say for the substituent we need locant number plus prefixes plus the root word plus primary suffix, that makes the name of an alkene. Locant number, prefix that may have a substituent or the side chain, and primary suffix that also should have locant number. That means we have to identify to which position the double bond is present, and the double bond that behaves as the functional group of alkene. Let us take an example, CH2 double bond CH2. This is the first member of alkene system. How many carbon it has? 2 carbon. So, I can write the root word of the 2 carbon is eth. And what about their bonding nature? Double bond. So, its primary suffix is ene. So, the name of the compound it becomes ethene. Its common name is actually ethylene. This is common name. This is IUPAC name. Suppose if I increase one alkyl group to the structure, I told the hydrogen atom of hydrocarbons are replaceable and that can be substituted by any kind of group. Now I am going to replace one of the hydrogen from ethane by methyl group. So what I will get? CH3, one hydrogen less, so it goes CH, double bond CH2. So in this structure how many carbon I have? 3 carbon I have. So the 3 carbon that makes the root word of prop. So I can write prop. And the primary suffix is ene. So the name is propene. Its common name is propylene. Let us add one more methyl group to the other carbon, opposite second carbon. So let us write CH3, CH double bond, CH, CH3. Now you see, you find 4 carbon atom. In this you can arrange their carbon in the numbering pattern. So you can write 1, 2, 3, 4 and 1, 2, 3, 4. So on either of the direction, the double bond it takes the second position. So the name, how many carbon I have? 4 carbon. So its root word is but. Where the double bond is present, second place. So but 2. What about its primary suffix -ine? So the name is but2-ine. If I write the isomer of the structure, I can take CH3, CH2, CH, double bond CH2. So both of them, they have the structure of C4H8, but one it takes but2-ine name, the other one the double bond is present at its first position, so the name it is into but1-ine. And the 2-1 you can even write in front of the name, but you can write in between of that suffix part and the root part, in between you can write its position of double bond. Similarly, you can write, suppose if I write CH3, CH, CH3, C double bond CH2. This CH3, CH2, CH that makes a branched one. See, I have 3 carbon in a chain, that is into a branched one. Once again, I found 3 carbon, but is not in chain, it is in a branch. So, such a structure is said to be iso. The name that can be given isobutylene. The common name is isobutylene. What about its IUPAC name? Numbering. First carbon, second carbon, third carbon. Why I have given first carbon to C double bond? Because the double bond is the functional group that should get a least number. So 1, 2, 3. And the second carbon it has methyl substituent. So the name it becomes 2-methyl. How many carbon in a chain? 3 carbon. So I should write prop. Where the double bond is present, first position. So prop1-ene. See, when you write the name should satisfy the total number of carbon in a given compound. I have 4 carbon in my structure. You can able to cross check whether I have given 4 carbon in my name. See, prop, how many carbon? 3. Methyl, 1 carbon. 3 plus 1, that makes 4. My structure is also having 4 carbon. So, you can confirm your name is correct. So, for the given structure, how many carbon it has, that many carbon should be counted in your name as a part of substituent as well as a part of chain. Okay, let us take. What about the previous one? Whose name is? It is butylene. Suppose if I have a double 2-pi bond, that means it has 2 double bond. I can write CH2 double bond, CH double bond, CH2. So it has a 2 doubly bonded system in its structure. So I have to identify both the position of double bond. So I am taking 1, 2, 3, 4, or in the opposite direction also 1, 2, 3, 4. So the name, how many carbon I have? 4. So I should write but. And how many double bond I have? 2 double bond. What are their position? 1 and 3. So I should write 1, 3. How many double bonds are there? 2 double bonds. So di. What about its primary suffix? -ine. Butadiene. So here I should add the letter A along with diene. But in the previous cases, you may find I have write prop, but or eth. I didn't take ethane. That is A letter I didn't take. Here why should I take? Because that diene, the first letter it commences with the consonant. So I can add the vowel over here. But in the previous cases where the vowel and the E letter, both of them are vowel, they do not come together according to rules. That's why where the double bond is singly present, you have to drop the letter A and you should write ene alone. But the system when it has more than one double bond, where they are said to be alkadiene. Or you can write if they have a 3 double bond, that will be alkatriene. So similarly, we can write the name for any length of the alkene system. The next topic is isomerism. Isomerism, same molecular formula but a different structural formula. They have similar methods of preparation, but they do differ in their physical properties. Chemical properties almost they will have same. And isomerism, let us take the compound C4H8 C5H10. C4H8, I can write the chain isomerism CH3 CH2 CH2 CH double bond CH2. So 1, 2, 3, 4, and I can write the chain isomerism, the 3 carbon that can be written like CH3 CCH3 double bond CH2. And one more we can write, that is CH3 CH double bond CH3. So this is structure 1, this is 2, this is 3. When you compare the structure of 1 and 2, you are finding the difference in length of alkyl chain, that is the alkyl part. So these 1 and 2 structures referred as chain isomer. So 1 and 2, it gives rise to the chain isomer of alkene. Now you compare the position of double bond with respect to the structures 1 and 2. Both 1 and 2, they have their double bond at the first carbon. But in the structure 3, you may find the position of double bond at 1, 2 or 1, 2. So the double bond is present at its second position. So with respect to third one, I can write 1 and 2 are chain isomer, and the third that exhibits position isomer. So position isomer arises due to the difference in position of double bond. Let us take the other molecule C5H10, for which we can write CH3 CH2 CH2 CH double bond CH2. Here I have given a long chain of 4 carbon that can be into CH3 CH CH3 CH double bond CH2. So once again I am having a long chain of 4 carbon with the other structure has only 3 carbon in its structure. So these two give rise to chain isomer. And I can change the position of double bond. So I can change it CH3 CH2 CH double bond CH CH3. These two make a chain isomer, for which we can write the position isomer as CH3 CH2 CH double bond CH CH3. When you change the position of double bond either to this carbon, once again 1 2 only it repeats. So this gives rise to pent 2-ene, and the first one, it has a double bond at first position. So this is pent 1-ene, and in the second case the double bond is at the first position and the alkyl group at its third position. So the name is 3-methyl. How many carbon in the chain? 4 carbon. So but, where the double bond is present at the first position. So it is but 1-ene. So this is what the isomerism. For a given compound, you can write so many structures, depends on the number of carbon in it. And from this, if carbon increases, you can make that alkyl part as primary alkyl part, secondary alkyl part and tertiary alkyl part successively. As well as you can make the double bond to change their position also. In isomerism, we have geometrical isomerism. The previous one we discussed about structural isomerism. Now let's take geometrical isomerism. This geometrical isomerism already we have discussed in detail. Just I would like to add some more points. Let us find the dipole moment of geometrical isomerism. So let's take CH3, CH double bond, CH, CH3. So the compound, it has a doubly bonded system that will undergo restricted rotation. Because of restricted rotation, the groups with the other carbon that can change its spatial arrangement. So we can write hydrogen CH3 for this carbon, and the another doubly bonded carbon has hydrogen and CH3. So when same groups are of same side, then the isomer is said to be cis isomer. If I rotate this double bond, it undergoes a restricted rotation only. It has no free rotation, just that of alkanes, because alkane carbon single bond, because here we have double bond. So when it rotates, I will get carbon hydrogen CH3. This it changes to CH3H. So this is what trans isomer. And I discussed in that link, the cis isomer has higher dipole moment than trans isomer. How? Carbon-carbon double bond, both of them are sp2 hybrid orbital, and the electronegativity of doubly bonded carbon is greater compared to the sp3 hybrid orbital of CH3 group. So as it has a greater electronegativity, the CH3 group that pulls towards the carbon, and this CH3 also that moves towards the carbon, and both the direction of the movement of electron to the same side, then the resultant dipole moment will also be to the same side, and hence the cis isomer, it has higher dipole moment. It is found to be 0.33 dBi. The unit to measure the dipole moment is dBi. Here CH3 group are of diagonally opposite to each other. So this CH3 it moves towards sp2 carbon, and this CH3 that moves towards sp3 carbon. See, the direction of movement of electron is just opposite to each other, because the dipole moment is a vector quantity. We have to consider both magnitude as well as the direction. Here the direction is same, and hence both the magnitudes sum up to 0.33 dBi. In this case, the methyl and the other methyl are just moving towards the carbon in the opposite direction. So both their magnitude gets cancelled. That's why trans isomer, it has 0 dBi. That is, the dipole moment is equal to 0 dBi for trans isomer. And already we discussed the carbon, both the doubly bonded carbon at least should have two different. So what kind of compounds they can exhibit geometrical isomerism? Either CXY double bond CXY. See, both carbon have similar group, or the doubly bonded carbon can have CXY with CXZ. Here one of the group is similar but the other group is different, or we can write CXY double bond C some WZ. Here both doubly bonded group, they have four different group. So such kind of compound alkene system can exhibit geometrical isomerism. Let us see the preparation of alkenes. Alkenes can be prepared from alkynes, alkyl halides, vicinal dihalides, alcohols, and from Kolb's electrolytic method. Let's take from alkynes. Alkynes are a doubly bonded system. So we can write C triple bond C. When it adds with one more mole of hydrogen H2, that may give rise to CH double bond CH. So a triple bond is reduced to double bond. For this we can make use of Lindlar's catalyst. The Lindlar's catalyst is palladized deactivated charcoal or palladium supported on calcium carbonate, which is deactivated either by sulfur or by gasoline. So we can have palladium with charcoal, where the charcoal is taken to deactivate the palladium, or we can have palladium in calcium carbonate that gets deactivated either by sulfur or by gasoline. Why we have to deactivate the palladium? Palladium is a metal that can hold a large volume of hydrogen. When the amount of hydrogen on its surface is greater, it would not give rise to alkene, instead it will go to alkane. but we need to prepare alkene only. So to stop the reaction up to the formation of alkene, the activated metals gets deactivated either by adding a charcoal or getting deactivated by sulfur or gasoline. This is why we are saying the palladized deactivated charcoal. So deactivation means that it behaves as either the charcoal or the sulfur or the gasoline, that it behaves as catalytic poison for the catalyst. So Lindlar's catalyst, either palladized charcoal or palladium supported on calcium carbonate deactivated with the sulfur or gasoline, that it gives rise to alkene. So we can have CH2 double bond, CH triple bond CH plus hydrogen in presence of palladium or carbon, or with this we will get CH2 double bond CH2. This is the step to which we have added the hydrogen. So this is called hydrogenation of alkynes. The next one from alkyl halides. Alkyl halides are, we can have CH3 CH2 Br. This is bromoethane. When it is treated with alcoholic potassium hydroxide, this alcoholic potassium hydroxide, you know the alcohol, it is less polar in nature for the ionic compound of potassium hydroxide. This makes the compound to undergo elimination. The elimination, it takes place between alpha and beta carbon. Alpha carbon has the bromide halide ion and the beta carbon has hydrogen. In this, one of the hydrogen from beta carbon getting eliminated with the halogen from alpha carbon, and the elimination of both hydrogen and halogen takes place simultaneously. So we will get CH2 double bond CH2. And the hydrogen with the OH that makes water, and the halogen with the potassium that makes KBr. So the reaction we can represent like this: CH3 CH2 Br. It goes such a way. So I am getting CH2 double bond CH2. See, we are removing two groups from the adjacent carbon atom simultaneously, and hence the single bond is into double bond. This reaction is known as beta elimination or even dehydrohalogenation, removal of hydrogen as well as the halogen. The next method from vicinal dihalides. What do you mean by vicinal? Vicinal means the halogen are in adjacent position. CBr CBr. When the two halogen atoms are in adjacent position, that is said to be vicinal dihalide. So we can write CH2Br plus CH2Br. So this is 1,2 dibromoethane. When this compound is treated with zinc metal, the metal is highly electropositive, so that makes the compound as ZnBr2 plus CH2 double bond CH2. Ethane is formed. So by treating vicinal dihalide with the metal, it gives the metallic halide and alkane. The next one from alcohol. Alcohol, we can have OH as the functional group. That alcohol undergoes actually dehydration reaction. From alkyl halide, we made it as dehydrohalogenation. One hydrogen, one halogen removed. But in dehydration, one hydrogen and one hydroxyl group to be removed. And this dehydration takes place within the given molecule. See, CH3CH2OH. When this alcohol is heated with concentrated sulfuric acid at 443 Kelvin, this undergoes elimination of water from beta carbon, a hydrogen, and the alpha carbon, the OH. So I will get CH2 double bond CH2 plus water. And this water is being absorbed by the sulfuric acid, so we will get an alkene. And this reaction, it undergoes the elimination of water within the molecule. Such dehydration is said to be intramolecular dehydration reaction. So this is also elimination reaction, but it is carried out from alcohol in presence of concentrated sulfuric acid at 443 Kelvin. This undergoes intramolecular. Intra means within the molecule the reaction takes place. In similar way of alkyl halide, we can write CH2H, CH2OH. So this hydrogen, it moves towards the OH group. So we are getting CH2 double bond CH2 plus water. The role of sulfuric acid to absorb the water molecule, and hence the alkene formed will be stable, or else it will react together to form alcohol. That means hydration of alkene takes place in the opposite direction. So in Kolb's electrolytic method, we have to take sodium succinate. When it is electrolyzed, we will get the cation and the anion. Succinate ion and the sodium ions are produced. This succinate ion at anode, it gets into CH2COO minus, CH2COO minus. It has 2 electrons. First of all, the 2 electron is lost at the electrode of anode. And the 2 molecules of carbon dioxide is also liberated. So this bond, it moves such a way, so CH2 it gets into CH2 double bond CH2. So due to the removal of the 2 carbon dioxide group from the adjacent CH2 group, the single bond is into double bond. So ethene is obtained by Kolb's electrolytic method. The next one, properties of alkenes. Let us see the properties of alkenes. First of all, let us consider physical properties. In physical properties, we know the state of the hydrocarbon, they can exist in gaseous, liquids and solids. In alkene, only the first 3 members, ethene, propene and butene, able to exist in gaseous state. After butene, up to 14 members of alkene are existing in liquid state. Then later all other alkenes are in solid state, and the solids are waxy solids or soft solids. And these alkenes are in general, they are colorless and odorless. But ethene alone, it has a faint sweet smell. When you consider the melting point and boiling point in a homologous series, as the successive members increase by the CH2 group and the unit of 14 molar mass, boiling point and melting point also increases in the given homologous series. But when you consider the isomeric alkene, the straight chain, when it approaches the spherical shape, the area of contact decreases and hence the van der Waals forces decreases, where the boiling point also decreases. This is we discussed in alkanes also. And considering the solubility, it has a least polarity in its structure due to the pi bond. So they are sparingly soluble in water. Sparingly means almost insoluble but slightly miscible. But these alkenes are highly soluble in organic solvents. Let us see chemical properties of alkene. The first property is hydrogenation. Hydrogenation of olefin is an important industrial process in which the edible oils are converted into vanaspati. Vanaspati is an artificial green. So the edible oils, they all contain an unsaturated system. That unsaturated system is getting into saturated compound in presence of nickel, platinum or palladium as a metal catalyst. So let us take an example, CH2 double bond CH2 ethene. It undergoes addition of hydrogen in presence of the catalyst like nickel, platinum or palladium. The ethene is converted into ethane. So the molecule of hydrogen is being shared between the doubly bonded carbon atom. So we are getting the saturated hydrocarbon. Such a way, in industrial processes, the edible oils of unsaturated system is converted into the saturated form of vanaspati. Next property is addition of halogen or halogenation. Halogens are generally represented as X2. Here we are going to take bromine, iodine and chlorine only. And the molecule of bromine, chlorine, iodine, they can add to a doubly bonded system to form, for example, if I take chlorine, I will get CH2Cl, CH2Cl. Or if the compound is treated with bromine in water, it gives CH2Br, CH2Br. Or in presence of iodine, it gives CH2I, CH2I. So out of these vicinal dihalides, see the halogen is in with the adjacent carbon atom. So when two halogen atoms are in adjacent position, they are said to be vicinal dihalides. So it forms 1,2 dichloroethane. This is a stable compound. When you have bromine in water, actually it is in reddish brown color. When it is added to an unsaturated system, the disappearance of reddish brown takes place. That means reddish brown color disappears when bromine is added to a doubly bonded system. So this is termed as test for unsaturation. So we can take bromine water to identify whether the given hydrocarbon has a multiple bond system. And then when ethene is treated with iodine, it forms 1,2 iodoethane. But this compound is highly unstable. This is because the bulky nature of the two iodine atom, when they are in adjacent position, that experiences a great steric effect. So due to its steric effect, immediately the iodine is being eliminated from the adjacent system and it gets into ethene plus iodine. So iodination of alkene once again gives ethene due to its less stable or the least stability of 1,2 diiodoethane. The next reaction is hydrohalogenation. In hydrohalogenation, the doubly bonded system can undergo addition of hydrogen halide. We have two different systems of alkene. One is said to be symmetrical system. The other one is said to be unsymmetrical system. What do you mean by symmetric and unsymmetric? About the double bond, if you have equal number of carbon and hydrogen on either side of it, such alkenes are said to be symmetrical alkenes. See, doubly bond left and right, they have both CH2 group only. They are in equivalent. But in an unsymmetrical alkane, about the double bond, you may find a different number of carbon and hydrogen. In this case, you have CH2, but in the left side, you are finding a methyl group. So, when uneven number of carbon hydrogen present between the doubly bonded carbon system, such alkenes are said to be unsymmetrical alkane. The symmetrical alkane simply it undergoes addition of hydrogen halide, where the doubly bonded carbon that shares with the HBr such a way. CH2 with the negative charge, because it undergoes, for example, if I have a doubly bonded system in presence of a nucleophile, I have Br minus. So the compound which attacks the nucleophile that attacks the carbon, simultaneously the pi bond that moves towards the adjacent carbon. So I am getting the reacting species of CBr with the negative charge over here. So to the negative charge of carbon that gets attracted by the H plus group, that is the electrophile. So this doubly bonded system, it gets added with H and Br. Let us discuss about Markovnikov's rule, in which the negative addendum of the groups that attack the carbon-carbon double bond system, where the more alkyl group is present. So we have taken propene, So the first step of the mechanism is the formation of carbocation. Carbocations are the carbon with the positive charge usually behaves as electrophile. So from the hydrogen halide, the H plus ion that attacks the doubly bonded system either to the CH2 carbon or to the CH carbon. When H plus goes to CH2 carbon, I am getting a secondary carbocation because the pi bond that attacks the H plus, thus the electron density of the middle carbon decreases and hence it develops a positive charge. Or the CH2 carbon that may attack that H plus ion, the CH carbon that may attack the H plus ion where CH becomes CH2 and hence the electron density of CH2 decreases, so getting positive charge. So among the formation of secondary and primary carbocation, we know well the primary carbocation is less stable than the secondary carbocation. So the secondary carbocation upon nucleophilic addition it gives a major product, but the primary carbocation will give rise to a minor product. So let us take the secondary carbocation to which the nucleophile attack that CH plus where we are getting 2-bromopropane. But in the less stable primary carbocation, if at all attacks by the nucleophile Br minus, it gives a 1-bromopropane. So the primary compound is a minor compound and the secondary or the tertiary compound will be the major in Markovnikov rule. So in this case, I have taken only CH propene structure. Suppose if I have a tertiary structure, how the reaction will proceed? Let us take the other example 3-methyl-but-1-ene. In this case, as a result of the compound we may expect to form the secondary product, but actually this compound will give a tertiary product. This is because the secondary carbocation which is formed will be converted into tertiary carbocation, the more stable one. So if a compound, if it has a tendency to convert secondary carbocation to tertiary carbocation, then the expected product will be the major tertiary compound only. So let us discuss how it takes place. So this compound, first of all, the formation of carbocation it gets. See the pi bond that moves towards the H plus, so the CH2 is into CH3 and hence the CH group gets the positive charge. So this is what secondary carbocation. And this secondary carbocation, very next to that you may find a CH3 twice group. Suppose if the hydrogen atom of that tertiary group migrates towards the secondary carbon, you may get this carbon will become a tertiary one. So this is possible upon the shifting of CH group, the adjacent the carbon from adjacent carbocation, the hydrogen shifts over to CH plus, that is the secondary carbocation that makes the positive charge over the hydrogen. So the bond here it breaks, we are getting the positive charge gets on tertiary carbon. So due to the proton shift, a secondary carbocation can even be converted into a tertiary carbocation. Similarly, instead of a hydrogen is there, we can even make a methyl shift. Instead of proton shift, we can do methyl shift, where also you can have a tertiary carbocation. That will be explained in the another topic. So if there is a chance of getting a tertiary product, we have to convert the secondary carbocation into the more stable tertiary carbocation. So we will get the tertiary product of the compound. Let us explain about anti-Markovnikov rule or Karash effect or peroxide effect. This rule is just against of Markovnikov rule. So in this case, the negative group, that is the nucleophile, will add to the primary carbon, not to the secondary or tertiary carbon. So here it goes to the nucleophile to the carbon with less alkyl group or no alkyl group, and it follows a free radical mechanism, free radical addition mechanism. So this reaction is possible only in presence of peroxide. Wherever you find peroxide in the addition of hydrohalogenation, you have to think of peroxide effect and the product will be primary. So let us take first of all the benzyl peroxide. It undergoes homolytic cleavage. The peroxide linkage is, this is oxygen-oxygen linkage is called peroxide linkage. So this peroxide linkage undergoes homolytic cleavage. You will get 2 molecules of benzoate free radical, and from which the carbon CO group and the C, it gets cleaved into homolytically. You are getting 2 times of phenyl free radical and 2 molecules of carbon dioxide. That is, the oxygen with 1 odd electron and the carbon gets 1 odd electron, that combines to make a bond. So you are getting carbon dioxide. Now this free radical phenyl that reacts with HBr homolytically to form benzene and Br free radical. So this bromine free radical is now the attacking species for our doubly bonded system. So this Br free radical, it attacks alkene. It may give rise to either a more stable secondary free radical or the less stable primary free radical. So the Br that can undergo homolysis with alkene system. Homolysis, once again the pi bond that gets split up such a way. So the dot, the 2 electrons, it may go to either the primary carbon or to the secondary carbon, depends on the attack of bromine free radical. If the bromine free radical attacks that CH2 group, you will get a more stable secondary free radical. Or if the bromine attacks the CH carbon, then the free radical formed will be less stable primary free radical. But the more stable free radical can give rise to the major product, and hence the secondary free radical of this compound, it undergoes homolytic cleavage with 1 more HBr to form 1 bromopropane. Plus Br dot will be formed. So plus here it has a bromine free radical. But in the case of the less stable primary free radical, that may undergo the reaction with HBr, upon homolytic cleavage it gives a secondary product, but the secondary product becomes the minor one. So we have studied about hydrohalogenation, a very important topic. It repeats even your higher secondary 12th standard also. So we have 2 rules. One is Karash effect or the anti-Markovnikov rule. The other one is Markovnikov rule. Both of the rule that plays exactly in opposite manner. So Markovnikov product always through the formation of carbocation intermediates, in which the tertiary carbocation more stable than secondary, which is than primary. So the more stable product will be secondary product or a tertiary product, depends on the nature of alkene. And in the case of anti-Markovnikov rule, the product is always primary and the reaction follows free radical addition reaction, in which the benzyl peroxide is taken as the catalyst, that is the reaction to proceed to form a phenyl free radical. So this is what hydrohalogenation. The next reaction is oxidation. Oxidation can be carried out in 2 different ways. One is with the mild oxidizing agents like Bayes reagent, and the other one the strong oxidizing agents like acidified potassium permanganate. In the 2 different cases, we will get different kinds of products. If the alkene is undergoing oxidation with cold dilute alkaline solution of KMnO4, it gives a dihydric compound. A diol is formed. That means the compound having 2 OH group, during which the pink color of potassium permanganate disappears. So this reaction is taken as test for unsaturation just like bromine water. So here, as the reaction carried out in a dilute manner, the water is also taking part. And because of the oxidizing behavior of KMnO4, oxygen is also getting added. So you may find the water, it has HOH group, and the oxygen atom with this hydrogen that can make OH group. So you have 2 times of OH group like this. So both of the OH group that adds to the doubly bonded carbon. So we are getting glycol. The name of the compound is glycol or 1,2 dihydroxyethane. It is generally called glycol. Actually its common name is ethylene glycol. Next, if the unsymmetrical alkene is taken with the strong oxidizing agent, that gives rise to carbonyl compound. Carbonyl compounds are either aldehyde or ketone. See, I have taken propene. The oxidation takes place between the doubly bonded carbon atom. So this CH2 part is oxidized into carbon dioxide and water. And the CH3CH is oxidized to ethanol or acetaldehyde. So I am getting ethanol, or its common name is acetaldehyde. So unsymmetrical alkene on oxidation gives carbonyl compound. What about symmetric alkene? Symmetric alkene gives carboxylic acid. So here I have taken butene. In this case also the oxidation takes place exactly between the carbon-carbon double bond system. So it breaks such a way. So this CH group is oxidized to COOH and this CH group is also oxidized to COOH. So we are getting the 2 times of ethanoic acid, or its common name is acetic acid. That's all. Oxidation. Oxidation reaction is useful for the test for unsaturation, to identify the double bond if you are using the Bayes reagent. Or you can able to identify the alkene whether it is symmetric or unsymmetric upon oxidation. The symmetric alkenes gives carboxylic acid and unsymmetric alkenes will give carbonyl compounds. The next property of alkene is ozonolysis. Ozonolysis is an important reaction by which you can identify the position of double bond in an alkene where the double bond is present, that we can able to locate. And if the alkene has a terminal double bond, terminal means at one of the end, if it has a double bond, then one of the product will always be formaldehyde, that is HCHO. Then if the alkene is symmetrical, it gives rise to 2 identical carbonyl compound. If the alkene is unsymmetrical, then alkene, it gives rise to 2 different carbonyl compound. Let us take how the ozonolysis reaction proceeds. This is a doubly bonded system, carbon-carbon double bond, to which a molecule of ozone is added. Ozone is an allotrope of oxygen, O3. So it gives rise to ozonide. That means the 3 oxygen atom that gets bonded with doubly bonded carbon as this system. See, you may find carbon, 2 of the carbon bonded with 3 oxygen atom. This is called ozonide structure. And this ozonide, when it is treated with zinc and water, it undergoes the cleavage of carbon, oxygen, carbon, this oxygen, oxygen, each bond. Here carbon, oxygen cleavage, takes place. Simultaneously, the oxygen-oxygen cleavage takes place. Similarly, to the other side, this carbon-oxygen cleavage takes place along with oxygen-oxygen cleavage. So, due to this cleavage, you may find they are getting 1, 2, 1, 2, 1, 2. So, there are 3 pairs of electron is formed. You may find the carbon and oxygen to the side, you are finding a pair of electron, one with the carbon, one with oxygen. Similarly, the other side, the carbon with 1 electron and oxygen with 1 electron you are finding. So, these 2 electrons that makes a double bond with carbon and oxygen, and this oxygen atom with water that left us hydrogen peroxide. So, in the ozonolysis reaction, the products usually carbonyl compound. The carbonyl compounds they are formed can be identical or different. If identical, then the alkene is symmetric alkene. If you are getting 2 different carbonyl compound, that is said to be unsymmetric alkene. So, let us take the symmetric alkene CH2 double bond CH2 ethene. Say this is symmetric, so it has to give rise to identical carbonyl compound. So, this ethene that makes ozonide structure with ozone. You have to write the structure more properly. So, all the carbon oxygen and oxygen bond breaks up, and the electrons of carbon and oxygen that makes a bond. So, we can write the structure like HC double bond OH. This is what the actual structure of formaldehyde. So, as the ethene molecule is identical, that is the symmetrical, I am getting the 2 same molecule of carbonyl compound, say formaldehyde. Let us take propene CH3CH double bond CH2. This is an unsymmetrical alkene, to which let me add ozone. So, I am getting CH3 to which C hydrogen and it makes the ozonide, and the terminal carbon it has 2 hydrogen. So, I am writing like, and this completes its ozonide structure. Later on, the bond breaking, that means here it breaks and here it breaks. Due to the breaking of the bond, you may find a set of electron between the carbon and oxygen and the set of electron between the other carbon and oxygen. So, it gives rise to this compound will be CH3. See, this makes double bond O with the hydrogen, plus this side HC double bond OH, or you can write formaldehyde. So, and unsymmetrical alkene, it gives the 2 different carbonyl compound. One is aldehyde, acetaldehyde, the other one is formaldehyde. That's all ozonolysis. This topic will also be continued in your second year, and here a compound can be given from which you have to identify where the double bond is present. For example, let me take a compound CH3 CO CH3 plus CH3 CHO. So, on alkene, upon ozonolysis, I am getting the product of acetone and acetaldehyde. From this product, I have to identify what would be the alkene. Let us do how it has to identify. Let us write the structure like C double bond O, CH3, CH3 plus this is CH3, C double bond OH. So, you have to write the carbonyl group together. So, these 2 carbonyl group that are formed as a result of the breaking of ozonide structure. So, now you are going to eliminate the oxygen which are obtained from ozonide. You can connect the double bond. So, you are getting the product CH3 double bond CH3. So, this is what alkene, from which the ketone and the acetaldehydes formed. So, the name of the compound is 1, 2, 3, 4. So, this is 2-methyl butadiene. So, from the given carbonyl compound, you should know how to identify the alkene system. And one more idea I can suggest. See, this is the alkene system. I have to identify what are the possible carbonyl compound. Nothing. Where the double bond is present, you add one oxygen to each and break the double bond. You will get the corresponding carbonyl compounds. This is an idea. Whether the products you got correct or not can be cross-checked with this. That's all was analysis. The next, let us see polymerization. What do you mean by polymerization? Polymerization is a process in which the monomers are, n number of monomers are converted into a polymer, a single unit of high molar mass. And the reaction is always carried out in presence of a catalyst at high temperature and high pressure. So here the one which is taken for polymerization, that reactant is said to be monomer. Once it undergoes either addition polymerization or condensation polymerization, lower molar mass of monomer is converted into a high molar mass of polymer. Alkenes usually undergo addition polymerization. Let us take ethene, propene and styrene. All of them, they have double bond. Addition polymerization means the double bond will be shifting. This N unit will be arranged in the linear chain. So, the double bond that gets linked between the two units of alkene, that makes a single bond. And the next double bond that shifts its pi bond to the another unit where the single bond makes. Such a way, the n number of alkenes arranged in a linear chain where the pi bond that makes link with the adjacent unit, and hence as a result of this we are getting polyethene. So, n number of ethene molecule I have taken, it gives rise to polyethene in which n times of ethene is present. And it is carried out in a red hot tube at the temperature of 873 Kelvin. If you take propylene, that is also passing through red hot tube at 873 Kelvin, it gives polypropylene. Or else the styrene, that means phenylethene. The name of the compound is phenylethene, that is called styrene. It undergoes free radical polymerization. That means it makes free radical in presence of a peroxide. So here it forms a polystyrene. So that's all the chemical properties of alkene. That's all the chemical properties of alkenes. Today we have seen about the structure of alkene, nomenclature, isomerism, preparation and properties of alkene. The last topic is uses. Alkenes, from which we have derived so many products like carbonyl compound, carboxylic acid, diols, alkyl halide, vicinal dihalide, these and all the products which were derived from alkene. So alkenes are useful in the preparation of the organic compound. And the polymerization, it plays a vital role in our daily life because we are depending on most of the plastics. The plastics we are using all are made from polymerization processes only. So alkenes, they play the most important role in the field of polymerization. So TV cable or the backlight, or we can say we have two types of polymers actually, thermosetting plastic and thermoplastic. Thermoplastics can be remolded, but thermosetting plastic cannot be remolded. So according to the nature of alkenes or the other compounds taking place in the polymerization, we will get the variety of polymers. So the next session, let us start with the new topic of alkynes. Until then, bye bye.